When we first began discussing the concept of equilibrium, I said that all reactions are reversible, or at least technically reversible. The reality is that sometimes this just isn't a reasonable assumption. For example, imagine trying to reconstruct the original reactants of a combustion reaction from carbon dioxide and water. One way of assessing reactions like this is to describe them as being very product favored. This means that while we accept the possibility of a reverse direction occurring, the forward direction is highly favored and the reverse is basically just a theory. In acid-base reactions, you will find that some reactions are like this as well. They're highly product favored. While some, others, achieve equilibrium a bit more equally placed between the two directions. As a result, to continue to study equilibrium, we're going to transition for the type of reactions we've been working with to focusing on how acids and bases achieve equilibrium. To begin with, let's review a little bit about what we know regarding acids and bases. First of all, there are these three definitions that constitute what an acid and a base is. They're the Arrhenius definition, Bronsted-Lowry definition, and the Lewis definition. If you look at them, you can see that the Arrhenius definition is the most specific. It narrows down the list of eligible compounds to ones that contain either an H+ or an OH-. The Bronsted-Lowry definition seeks to solve the problem of how there are some additional compounds which exhibit the same properties that we use to identify acids and bases, despite not necessarily possessing either of those ions. This increases the number of compounds that we are able to refer to as acids and bases. It is important to note, however, that a compound could fall under either definition, or it may also be both an Arrhenius acid and a Bronsted-Lowry acid. In the final definition, we see that the scope of what can be considered an acid or a base extends even further. Since an electron pair transfer is present in even a greater number of reactions, even more compounds may be considered acids and bases according to Lewis. The context of the situation determines which definition is the most appropriate. If you remember also, when discussing acids and bases in the past, we determined a list of compounds which are considered strong acids and a list of compounds that are considered strong bases. It is important to note that these lists were simply found in a textbook and memorized. If you remember, the definition of a strong acid was that it is an electrolyte. It dissociates in water 100% into its ions. This implies a very product-favored reaction. A weak acid, or a weak base, on the other hand, was one in which dissociation was not as complete. So in a solution of any weak acid or base, you would have a mixture of reactant and product. This is due to the reality of an equilibrium system being formed when weak acids or bases are put in water. Because their ions have such high attractions for each other, they may dissociate into new products, but may also reform into their original compounds by following either the forward or reverse directions. The type of reaction in which we originally discussed in this state of equilibrium most directly was the Bronsted-Lowry definition. Let's take a look at a Bronsted-Lowry acid reaction. If you recall, the water is the acid because it gives up the proton, and the NH3 is the base because it accepts the proton. Additionally, if you look at the product side and consider the reverse reaction, the NH4+ will behave as the acid as it has the proton to give up, so we'll actually call that the conjugate acid. And the OH- will behave as a base because a proton would solve its need for molecular neutrality. So we'll call that the conjugate base. This makes these two compounds into the conjugate acid and the conjugate base respectively. This was our original introduction into equilibrium back in the fall. Don't forget also that acids can be categorized as monoprotic, diprotic, or triprotic, depending on how many protons are part of the acid. Also, some compounds are called amphiprotic or amphoteric, which means that they can behave as either an acid or a base. All right, let's return to what we were saying previously about the strength of an acid and the strength of a base. Formerly, our way of interpreting these was A, memorizing the list of strong acids and bases, and then assuming everything else was weak, or B, using the pH scale as a general indication of an acid's strength. Okay. We've talked about the pH box before, and we've talked about how to use the arrows and go between the different types of compounds, whether we are talking about concentrations or whether we are talking about the pOH or the pH of a particular solution. The pH scale was a more useful way than just memorizing lists of making assessments experimentally regarding the strength of an acid or a base. It is a system by which the concentration of H+ ions in a system can be measured. Unfortunately, it's most useful when dealing with strong acids and strong bases because they dissociate 100%. Therefore, the given concentration of an acid, for example, would equal the concentration of the H+ ions. With a weak acid or a weak base, however, this is not a valid assumption. So if I were to tell you to calculate the pH of a 0.5 molar solution of acetic acid, it's not safe to assume that the H+ concentration would also be 0.5 molar. This makes sense, and it makes it difficult to predict what the pH would be, because you don't know exactly how much acetic acid will actually dissociate.